Hi, I'm Bradley Bush. Today we're going to talk about a classic problem dealing with the precise definition of a limit. If you've been given a function, a limit, a c-value, and an epsilon, can you find delta? So if we wanted to say this a little more mathematically, given f, L, c, and epsilon, find delta such that if the distance between x and c is bigger than 0 and less than delta, then the distance between f and the limit L must be less than epsilon. Maybe putting it in layman's terms, in English, if the distance between x and c is less than delta, then that means the distance between f and L must be less than epsilon. So this is the picture of what we're dealing with. And by the way, if you wanted to play with this picture, I made it in Desmos. You can go to desmos.com. It's a free online graphing utility that's fantastic. You can just write in the stuff I have there on the left and play with it. So let's get back to this problem. And remember, this inequality must hold. If the first is true, then the second must be true. So on the left-hand side, well, let's look at this one right here, actually. Let's look at this. Where is this inequality on the picture? The limit, we know the limit. The limit's right here. The limit is 0.5. We know epsilon. What is epsilon? Epsilon is 0.2. So if we take the limit plus epsilon, we get to 0.7, and if we get to take the limit minus epsilon, we get to 0.3. So the boundaries on the y-axis are 0.7 and 0.3. That is this pink interval right here. So what about this interval on the left? What about that interval? Where is that? Well, the first thing we have to note is that we don't know what delta is. We've got to find a delta that makes all of this true. And not just a delta, but we've got to find the largest delta that makes that true. So looking at our picture, we can see a bunch of deltas down here. Here are a bunch of deltas. Here's a delta and here's a delta. So we just have to find one. We have to find the biggest one that can fit in this region right here. And once we've found that biggest delta, then we can find our endpoints and we're done at that point. So you can look at this and you're probably thinking, I've got this. This is actually pretty simple. The biggest one is probably just this length right there, because you're saying to yourself, I can't use this length because that one, we know that the delta interval has to be centered at the c value. The c value is right here. So if I use this gray length on the right as my delta, that means my interval would go all the way out to here about, and that wouldn't work. Because if we took an x value out here, we shot it up to the function, came over to the y-axis, we would be above 0.7. And our inequality states that whatever x value we choose inside of these deltas on both sides of C, that x value has to be associated with the y value that's between 0.3 and 0.7. So this is not going to work. This one on the right. So we can see already that it's the one on the left. And if I drew the other one about the same length, it'd be something that look kind of like that. On the left-hand side, we can see that the left interval will be 1.429, but we don't know what the right one is. We could guess it because we know what 2, we can figure out what 2 minus 1.429 is, and that's going to be delta. And then we can just add that to 2, and we'd get our right endpoint. So that's really all we're doing. And if we look down here at the algebra, we can see that is exactly what we're doing. So our first goal with the algebra is to find this quantity. So the function is 1/2. The limit is 0.5, and epsilon is 2. We just plug them in, and now we just solve for x. Now we just have an algebra exercise. So to get rid of the absolute values, we need to have a negative 0.2 on the left and a positive 0.2 on the right. Then the absolute values drop. And now we need to get rid of the 0.5 in the middle. So if we add 0.5 to each of the sections, then the 0.5 in the middle goes away, and we have 0.3 on the left, 0.7 on the right. Now in the middle we have 1/x, and we just want x. So if we flip each of the 3 parts of the inequality, we have to change the direction of the inequalities themselves. So this inequality changes direction, that inequality changes direction, and we have 1/0.3 and 1/0.7 on the ends. Just doing the algebra, or just doing the arithmetic, 1/0.3 is just 3.333. 1/0.7 is just 1.4286. And personally, I like to see the biggest numbers on the right and the smallest numbers on the left. So I'm just going to spin this inequality. It still says the same thing, but it just has the small number on the left and the bigger number on the right. So notice this is actually interesting, because notice this number right here, 1.4286, that we just found algebraically. That's exactly the same number there. That's just rounded to 3 decimal places. So that means 3.333 is probably this number right here. So we just found those 2 x values that were associated with the y values of 0.7 and 0.3. We just found them algebraically. So the idea now is, which of these is closer to 2? Because remember, in our picture, we want this one that's closer to 2. We want this area right here. So we want this end because it's closer to 2. We don't want the 3.33 because it's further away. So if we just did a subtraction, 2 minus 1.4286, and then the 3.33 minus 2, we get the two differences. And we can see right away that this one is the smallest one. And that's the one that we assign to delta. So 5714, that is actually this distance right here. 0.5714. That's what that delta distance is. And also this other one on the right as well. So now we just build the interval because we need the two endpoints. We already know the right endpoint, or the left endpoint, sorry. We know the left endpoint, but we can find it algebraically by 2 minus the delta. And we can find the right endpoint by doing 2 plus the delta. And that's our answer. And of course, our delta that we chose was 0.5714. Thanks for watching.